As you might be aware by now, Vellum is a system of particles and constraints that string together those particles and drive how they behave in the simulation. What sets Vellum apart from grains is the versatility of those constraints. So let's have a closer look at the individual constraints available in Vellum. What I'll do is drop down our standard grid and use that for most of our examples. Not all, but most. So there are different ways of creating those constraints, and the most common will be in SOP level, just using the Vellum constraint SOP, which has 3 inputs taken in the SimGeo, and let's also create a torus and scale it down like this as a collision geometry. And by default, this constraint here is set up to be a distance along edges constraint. And let's just drop down a Vellum solver, highlight this, and maybe also enable a ground plane like this, ground position, and let's move it down 1 unit, and then hit play. And you can see this pretty much looks like a very flexible cloth. The reason why it looks so flexible is that it does not enforce any bend constraints. That means it only takes care of the mesh's individual points not moving away further or closer together than their initial distance. That's all the distance constraint does. Just going to copy all those nodes, paste them, and reset my scene here. And let's have a look at the other constraints that we have here. We have the bend across triangles. And let's just enable this constraint and see what the simulation does. We can see there's weird stuff happening, weird stuff going on. That is because bend across triangles tries to preserve the angle between individual mesh triangles and not necessarily the point distances. So we get these weird points that move about while somehow trying to find point positions that satisfy this constraint. That means keeping the angles between mesh triangles. Well, what happens if we combine this bend constraint and let's add another Vellum constraint down here with a distance along edge. So now we have both constraints on bend and on the distance. Now we hit play. Well, what we just built ourselves is a cloth constraint. So again, let's copy those first 4 nodes here, reset our sim and highlight this. And this time I want to set my constraint here to cloth. And what cloth does is it builds a constraint network both for the distance and also for the bend across triangles, called stretch and bend in here. So when we hit play, we can see this is behaving really similar to what we built here manually with the bend and distance constraints. Let's wire in a null object here and connect this to the constraint geometry. So the middle slot here, the pink slot here, will carry our constraint geometry. And let's head over to the geo spreadsheet, go to primitives here, and here we can see the attributes that are stored on those constraints. So with our constraint set to cloth, we can see we have a distance constraint, but we also have a bend constraint here. And each of those individual primitives stores the attributes for each constraint, such as the rest length or the damping ratio. Also, when we go back to the scene and highlight our null, we can see this is the constraint geometry that we built. So basically what we are building here are those alternating triangles between those individual points, which then get moved around. And you can influence how this geometry is built up here in the geometry section, and you can choose triangulation mode. So we've got none, regular, or the standard setting of alternating, which will form those triangular shapes here. And for later, keep in mind that to drive the simulation behavior, we might want to influence the parameters on those primitives, such as the stiffness, rest length, or damping. But for now, let's reset this sim again and copy it one more time, and set our constraint to hair. And for hairs, I need some polylines, not a polygonal mesh. So I'll set the grid's connectivity to rows here, so I get those strands with those individual points here. And when I hit play now with the constraint set to hair, we can see we get those strings falling down, as if they were made of strings, hairs, wires, whatever you like to call it. Again, looking at our constraint geo here, you can see we have 2 different types of constraints. A bend twist constraint, which enforces a given angle between adjacent points, so they don't become super flexible. But also they enforce a given twist constraint, so the hair or strings do not twist within them. And also we have a stretch and shear constraint, which is there to enforce the point distance. So here you could drive how rubbery, for example, your strings would be. Copy this one more time, again reset our scene, and in here let's set our constraint type to string. Hit play again, And that looks pretty similar to hairs. So what's the difference? Well, when we look at the constraint geo and geo spreadsheet again, we can see this time instead of a bend twist and stretch shear constraint, we got a distance constraint and an angle constraint. So here we are not constraining the twisting of each individual string. They are allowed to move freely around their own axis. And also we have much cheaper constraints. And by cheap, I mean computationally more easy. So the strings, in contrast to the hairs, will simulate a good bit faster. However, their constraints and thus their behavior is a bit more basic due to their simpler constraint types. Again, copy this, reset our scene. The thing with the next constraints is they are mostly only useful if you combine them with other constraint types. So in order to test what pin, texture geometry, stitch points, pressure, tetrahedral volume, weld points, glue, and struts do, we'll create a cloth constraint here, and we'll set our grid back to be a quad mesh. So we have this basic cloth behavior here, and then drag the solver down and create another vellum constraint, which I'll wire in between the cloth constraint and the solver, like this. So with our first constraint set to cloth, let's set the second constraint to pin to target. And what pin to target does is, when you hit play, the cloth does not move, because pin to target pins the simulation geometry, or the simulation geometry's constraints, to our incoming geometry up here. And we can also, and by default it is set up to pin this permanently, which is not as useful, I think. I find myself often using the soft constraint, where I can dial in the stiffness of these constraints. So now with their stiffness dialed up really high, again, the cloth just sits there at its original position. However, when I dial this back here to say 20, hit play again, I can see now this springiness, the springy effect of my cloth here. Because it's these constraints that basically act like springs that want to pull those points to their original position. And admittedly, this example, as it is now, is not really useful. However, we will see more useful examples later when we can use these constraints, for example, to dynamically pin points towards positions, or dynamically put them to rest so simulations won't jitter after a certain time. So pin constraint is just there to pin simulation points to a given position. Copy this one more time, reset our scene, and let's set our secondary constraint here to attach to geometry. And in the target path you can specify a geometry to which you'd like to attach your simulation mesh. I'll just use our collider here, the collision geo, torus. Let's have a look at the constraints we're building here. And we can see we just created those constraints here that just try to find the closest point on the geometry surface that we specified, and then just basically build a spring that connects or keeps those points apart from the surface. So when we highlight the solver here and hit play, we get this weird effect, which also collapses here and is not really that useful at all currently. However, similar with the pin constraint, the power of this attached to geometry constraint really comes when you build these constraints dynamically within your simulation, where they could be used, for example, to stick your simulated geometry to a collider as if it was made out of glue. But more on that later. So that was the attached to geometry constraint. Let's copy and paste this one more time. And let's set our secondary constraint to stitch points. Well, stitch points, I think I got a better example when we exchange this grid here with a tube. Let's set it to x-axis. Wire this in. Let's just highlight collider. Scale down our tube a bit, maybe like this. Increase the height a tiny bit and set it to be a polygon. 36 columns. Maybe 24 rows, like this. And now what I'm going to do is I'll just highlight a few faces and delete them. Like this. Just delete the grid here. And I'll need some groups to show you the power of stitch constraint. And I'll just do point groups here. And I'll just select, using that rectangle here, I'll just select all of those points, put them into one group, and then select those points, put them in another group. So we've got group 2 here and group 1 here. Before we enable the stitch constraint, let's just disable it, but let's rotate this tube a bit and hit play again. And you can see already, here we are opening up this gap. This gap simulates independently. So in some cases, for example, if you drape a cape around a running character, you would want to stitch together some points, for example, for the cape not to open up. And we can use the stitch constraint to do exactly that, and stitch together our 2 point groups that we selected. So let's do that by highlighting the stitch constraint, enabling it, and then we already set it to stitch points. Let's set the group types to points, and let's stitch group 1 to group 2. And you can see we are building those constraints here. So now if we hit simulate, you can see they are not the stiffest constraint because we set their stiffness to 20, which is a really low value. So let's set it to 2 million, resimulate again. And you can see now this area where we stitch together the points is kept apart in exactly the right distance that we had in our original geometry when we specified those constraints. So stitch is there to stitch together different groups of geometry, be it points or primitives. For our next constraint, again, let's copy the setup here, paste it, and in this case, what I want to do is just first delete all those groups we set up to stitch those together and increase the stiffness to the maximum. And then let's have a look at the pressure constraint here. And for that, let's, instead of our tube, use another torus as our simulation geometry, scale it down a bit and move it a bit off center. And maybe like that, increase the rows and columns, and wire it in our constraints here. So first the cloth constraint and then a pressure constraint. Let's highlight the solver and hit play. We can see here we have this behavior now, like some inflated balloon or inflated toy. So let's look at the constraint here that we build. Just disable the cloth so we can only see the pressure constraint that we built. And that looks a bit weird. I mean, it's those white lines that move around here and just somehow wind around this torus here. So let's have a look at the geometry spreadsheet. So again, this is the constraint geometry, and within the spreadsheet we can see this is only one primitive. It's of type pressure, as our stiffness, and within the rest length parameter, that looks weird, because this one stores the volume of the object that we fed it, and it tries to enforce this volume depending on the stiffness parameter. So we would use this one if we want to simulate geometry that is filled with a compressible gas, such as air or helium or whatever. Basically anything balloons or anything inflated. You want to use that. However, and let's copy this, there are other ways of making bouncy stuff in Vellum. For example, by using the tetrahedral volume. And what tetrahedral volume will expect is a tetrahedral geometry. That means when we look at our torus and clip away a good bit of the geometry, we can see it is hollow. However, what the tetrahedral volume constraint wants is a mesh that is filled with tetrahedra. So let's build one using the solid conform. Wire this in here, and we can see now the surface looks almost identical, except for those triangulated shapes now, but the inside has been filled with tetrahedrons, so with triangular shaped pyramids in a way. Let's disable clip here and highlight our simulation again and hit play. You can see it simulates a bit slower, it behaves a bit stiffer, but in general it's a soft body-ish type thing. So when would you use tetrahedral volumes over pressure? Well, basically when you have a balloon or an object filled with incompressible fluid, that is water or oil, or basically most liquids. It comes at the expense of higher computation times. However, if you're looking for this type of behavior, or if you have the feeling of that the pressure constraint is behaving too squishy and conserves your volume too little, then the tetrahedral volume would be an option. However, there's a third option of turning this torus into some wiggly shape. So again, reset the scene, copy all of this, and get rid of the solid conform and the clip, and set our constraints to struts. Let's look at the constraint geo we just built, and without the cloth constraints, we can see these are the kind of constraints that struts build, and it's a bit funny. What struts does is it just tries to look for the opposite point on a mesh and just connect those 2 points in order to do a really simple approximation of what a soft body is, which is opposing points just trying to push themselves apart with a spring. So let's just try this and highlight our Vellum solver. And you can see this simulates quickly, and it's got this soft body-ish behavior. It is not as good as being squished now with another geometry and then bulging at one side. That would be more the area where you'd use a pressure constraint or the tetrahedral volume constraint. However, for basic soft bodies that don't get squished around too much, this is a really quick and easy and rather stable way of simulating soft bodies. For the last 2 constraints, let's look at our basic cloth simulation again. I think it's this one here. Copy it and paste it down here. So that's our cloth sim. And the last two constraints are the weld points and the glue. Let's have a look at glue first. In my main geometry, let's just drop down a merge here and use a transform to offset our grid and then merge it back with the original grid, and then just move this grid to the side a bit, maybe like this, and a bit along the y-axis. So now we have those two close by grids here that are not connected yet, and let's just disable the second constraint here, hit simulate, so we can see what happens without a glue constraint. So we can see the second cloth just slides down from the first cloth and just lays there flat on the ground plane. Let's enable the glue constraint. And what glue will do, and you can see this already here, is it will look for nearby points within the simulation geometry that are not on the same piece, so it won't connect to itself. It will just connect to pieces close by. And you can dial in the maximum search distance like this, or the maximum number of points to search. The constraints per point, you could increase them to make them stiffer. But basically, the setup as is fine for now. I'm just going to increase the stretch stiffness to be very high, and then highlight the solver again and hit simulate. And yes, I maybe should have enabled the cloth constraint first. Okay, simulate again. And you can see now both of our cloth pieces are connected here, and this piece drags down the other piece. Again, this is one of those constraints that you wouldn't typically use like this. You would rather build these constraints dynamically, so that pieces of your simulation geometry stick together when they hit while they are flying around your scene, for example. Something we will build later. For our final constraint, again, copy this one last time, and let's get rid of the merge here and the transform. But instead, drop down an edge fracture. And edge fracture, let's wire this up, highlight it, and check primitive pieces. Then click on the info symbol here. That's new in 17. When you click on the piece attribute name, you can see the attribute visualized automatically here in the viewport. So what we did is we basically fractured this cloth into individual pieces. And let's just disable the secondary constraint and just simulate this. And you can see as soon as we're hitting any colliders, those pieces of the cloth, they just tear apart. Because they're not connected. It's just by accident that they are close by here and still look connected. But basically they are just individual pieces. And that's where the final constraint comes in really, really handy, which is the weld points constraint. So what we're doing here is we automatically stitch together adjacent points that are on different mesh pieces. And this is one of these constraints that is exactly built for that, tying together pre-fractured geometry to make it appear as if it was unfractured and one single piece. So when I hit play now, and move this to the side a bit, you can see we now have the appearance of a whole cloth again. But also, the weld points constraint comes with a neat feature called breaking. So we can specify a given stress measure here, and if this stress level is reached, and if it is above this threshold here, the constraints will just be disabled, and it will look as if the cloth would have been torn there due to the stress. So let's maybe dial this down a bit and hit play again. Just highlight this. Not enough stress reached here, so let's reset this, and on the weld constraints let's dial back the threshold even further, resim this, and now we can see as soon as it hits Collider Geo, it tears apart. So with a bit of tweaking, maybe we can make this look more interesting. Yeah, now we've got only certain parts of this geometry tearing apart while others still stick together. So that is the weld constraint. So with that, I think we had a look at all the constraint types that are there by default in Vellum. And as I mentioned, some of them are more useful when they are used dynamically. That means while the simulation or a simulation is running. And that's what we're going to look at in the next tutorial. So see you then.